Good morning, chemists. Let's get started. A reminder that, last week was our midterm week in recitation. This Friday, so tomorrow, recitations are back to activity days that are just graded for attendance. We'll have two recitation activities. So this week is number 4. Next week is number 5. And then on the third week, that will be our midterm 2. And I will have another review session that week, and so we'll talk about that then. So basically 2 recitations, then a midterm. Okay. All right, so we left off learning about ice tables in chemical equilibrium last class. I related the usage of ice tables similarly to BCA tables from Chem 1210, where we looked at limiting and excess reactants to predict the amount of products that we make. But in those kinds of reactions, the BCA tables, those reactions went to completion. But for equilibrium reactions, these reactions don't go to completion. Both sides of the equation exist at the same time. So we use an ICE table that stands for initial conditions, how the reaction changes to achieve equilibrium, and then E stands for the concentrations at equilibrium that you put into your K expression. So we looked at some examples of our type 2 ICE tables where I give you initial conditions, I give you K, and you have to solve for equilibrium concentrations. Often that requires us to use the quadratic formula, but I showed you some tricks that sometimes you don't need to use the quadratic formula when we use an approximation. And so I'll remind you what that approximation is. So, we did our ICE table. We're given K, we put in those equilibrium concentrations with the X terms in it, and we get a value or a expression that looks like this: X squared over 0.1 minus X equals a tiny K value. This, if we solve this, does require the quadratic. So our thinking here is, okay, we can simplify this if we just use logic. This minus X term is saying, oh, you're consuming a little bit of your reactant to produce product. But tell me, is this K really big or really small? It's really small. So if it's small, what is most present at equilibrium, reactants or products, if we have small K values? It's mostly reactants. So what we see is that when we move this reaction forward, it doesn't go forward that much. It's just we only lose a little bit of that A value. So we can say that this minus X term is really, really small compared to what we're subtracting it by, that this is a pretty large number. And so what we can do is just get rid of that minus X. Because if we subtract a really, really small number from 0.1, will that value, 0.1, change a lot? It won't change that much. So that's why this is a valid approximation, and we proved it to ourselves where we did the calculation without that minus X terms. This is using the approximation where we're just saying, okay, 0.1 minus X basically just equals 0.1 because X is really small. And we see that these answers are essentially the same. So that would be a valid approximation. We're going to be using this approximation a lot in chapter 16. So just keep that in mind. We did 2 different examples that use the approximation where we're able to get rid of the plus or minus X in the denominator because that's what screws us up with the quadratic. And we see that the answers using the approximation does work out. And so we left off in this question. It's still a type 2 type of ICE table where I give you initial conditions, I give you K, and so let's calculate equilibrium concentrations. So we partially set this up. Am I using the right slide? Yes, I am. Okay. So let's back up a little bit here. We're given initial concentration, so I'm telling you, okay, we have half the ATM, so partial pressures here of our 2 products. Right? We predicted, because there's no reactants, this reaction has to go into the reverse direction. So in our change line, we're saying we're going to lose an X amount of both of our reactants, but gain a plus X amount of our reactants. And so yes, the reaction is moving in the reverse, all right? It doesn't mean that we have to flip the reaction. We can just plug in these equilibrium concentrations into our K expression, how the reaction is written, because Kp in this example is given using this equation, which is written in the forward direction. So we know that Kp, that is this 100 value, is equal to pressure of A2, pressure of B2 over our partial pressure of our AB reactant squared. That 100 value is related to the reaction as written in this forward direction. So we want to keep it that way. Even though the reaction's moving in the reverse direction, our strategy here is still the same. We want to put those equilibrium concentrations into our K expression. So once we get the change line correct, we add up all these columns and we see 3 different values that we can put from our equilibrium line into our K expression. So I can write that out as 100 equals 0.5 minus x, but I do that twice, and I do that twice and multiply them together. So that's the same thing as saying 0.5 minus x squared, right? Because it's the same number multiplied twice, over the the equilibrium concentration of the AB reactant. So 2x, but that whole thing has to be squared. All right? So, does this require the quadratic? So at first when you look at it, it does look quite complex. There's a minus x term in the numerator and it's all squared, so you might want to distribute that square. All right, and then that might require the quadratic, but we don't actually have to use the quadratic here. We can be sneaky. Do you want to be sneaky? Yes, let's be sneaky. So we have 100 equals a value squared over a value squared. So what do you think we can do to simplify it? If we take the square root of both sides. Do you know the square root of 100? It's 10. Yes, it's 10. Equals, so if we take the square root of both sides here, that square on the numerator and the denominator go away. They get canceled out. So we get that 10 equals 0.5 minus x over 2x because we are able to get rid of those squares. So does this require the quadratic? No, it doesn't. That is just like regular algebra that you could just rearrange things and figure out what x is. So this is an example of using ice tables where we actually don't have to use the quadratic if we notice that we have a square value over a square value. This is called a perfect square, where you can just take the square root of both sides and simplify everything here and avoid using the quadratic. So I'll prove to you that I know how to do math. So I'm going to multiply both sides by 2x. So on the one side, we get 20x equals 0.5 minus x. See, it doesn't need the quadratic. And so we combine those x terms, and so we get 21x equals 0.5. And then so we get that x equals something. I don't know. Did I write it down? Come on, did I write it down? Yes, x equals 0.0238 atmospheres. All right, so we were sneaky. We were able to utilize the idea that given this, how we set up our K expression with those X terms, we ended up with a perfect square where we could square root both sides and simplify the expression so we did not have to use the quadratic here. All right, X, is that our answer? No. So we got to look back into the context of the question to see, okay, what is the question actually asking for? It's asking for all of the equilibrium concentrations. So how do I get that? Using the answer I just got. We want to plug that X back into the E line for all of them. All right. So if you plug that X value back into the E line, our two products lose an X amount of pressure. So I think these values are like 0.4 something. Oh, I have them in the corner. 0.476 atmospheres. That's the pressure of A. A2 and B2, both of them have the same partial pressure. And then the partial pressure of the AB reactant is just 2x, so it's 0.047 atmospheres. All right. And so if you want to check yourself if this is correct, these equilibrium concentrations, or pressures, sorry, we can plug those values back into the K expression. So if you put in 0.476 squared over 0.047, you should get 100. Because those are our equilibrium concentrations, pressures here, and so it should equal the Kp value that's given for this reaction. So that's a way to check yourself if you're calculating those equilibrium concentrations. All right, so you can check that and see, yes, you do in fact get 100 come out, so you can be confident that your X value you calculated is correct. All right, so that's the last kind of ICE table within this chapter, so we can put our calculators away for the rest of the chapter. So we're going to look at some other kind of consequences of equilibrium. All right, so we're still talking about K. We're also going to be talking about Q, so concentrations not at equilibrium, but we're going to predict what happens to reactions qualitatively, what happens qualitatively to reactions if we disturb them, how equilibrium have to basically react if we disturb some type of equilibrium. And so this is called Le Chatelier's principle. So we're still going to be talking about K and Q, but thinking about it qualitatively. Someone asked me in 1220 what's my favorite chapter, and I said initially chapter 14, kinetics, because reactions go fast. I like that. But actually, I think it's this part of chapter 15 is my favorite, Le Chatelier's principle. All right, maybe because it's qualitative, I guess. All right, so just as a reminder, K, that value is only valid when we're at equilibrium. So if we're not at equilibrium, and I give you concentrations, is that K valid at those conditions? No. At those conditions, when we're not at equilibrium, we have to use Q to calculate the theoretical value of the ratio of products over reactants. So Q, I'll remind you, is the reaction quotient. It's the same equation or expression as K, it's just we're not at equilibrium, all right? So kind of our thinking here is, okay, if we're at some type of Q condition, how does the reaction have to change or adjust itself to achieve equilibrium? Because all reactions will tend to move in a direction spontaneously to achieve equilibrium. So when we're at Q, we're not at equilibrium, a reaction adjusts itself until it is. So basically both for K and Q, it's the same equation, products over reactants, use the exponents, but in one case we're at equilibrium, the other one we're not. We already talked about comparing Q and K and kind of how to predict which way a reaction has to go. I got a lot of questions in office hours about this, so maybe I'll just help us here. So let me give you some examples. If I tell you K is equal to products over reactants, right? And I have a large number over a small number. What kind of number comes out? A large number, yes, a large number comes out. But what if I calculate a Q value and I have a small number and I divide it by a large number? What kind of number comes out? A small number, yes. Okay. So what we can say at equilibrium, when K is a large number, if we have a large number, we need to take a large number and divide by a small number. So if K is large, what is mostly present at equilibrium? Products, yes, because products is in the numerator, reactants are in the denominator. But if I set up a reaction where I have a small Q value, how did I set up my reaction? I have not a lot of products, but a lot of reactants. So how can Q adjust itself to become K? If I make more products, it turns a small number into a large number, and then if I eat up my reactants, I turn that large number into a small number. So if the reaction moves in the forward direction, when Q is smaller than K. That's how we get these different responses. When Q is smaller than K, the forward reaction must occur. Again, if you remember, small over large versus large over small number. Or if Q is larger than K, I have too much products, so the reaction has to move in reverse. So this is kind of what we want to think about when predicting whether a reaction has to move forward or reverse to achieve equilibrium. All right, so yes, Q can tell us many things, how the reaction has to adjust itself to reestablish K. And so what Le Chatelier's principle says is just some qualitative predictions of how we can estimate this. So we're going to study 3 different ways we can change an equilibrium. First, we're going to add and remove reactants or products. So essentially, we have a system at equilibrium. Let's change the concentration of something. How does the reaction have to adjust itself? We're going to change pressures if we have like a all gas system. And then finally, we're going to change temperature. So those are the 3 things we're going to look at. Okay, so we're going to learn Le Chatelier's principle kind of 2 different ways. The first way is just the quick and dirty way. That's what I like to call it. And then we're going to learn conceptually what's actually changing at a particle level. So let's learn the quick and dirty way first. So Le Chatelier's principle says if we have a reaction at equilibrium, it's real stable right there. But then we're going to poke at it, change it, and then the reaction has to respond somehow to get back to equilibrium. And so the quick and dirty way is basically whatever you do to a reaction, to an equilibrium, the equilibrium has to respond, or the reaction has to respond in such a way to undo what you just did. Okay, so if we have a reaction at equilibrium, okay, it's chilling there. If we remove reactant at a certain moment, the equilibrium is going to adjust itself to make more reactant that you just removed. If you have a reaction at equilibrium and you add more product, the reaction doesn't like that, so it's going to adjust itself so it takes away that product that you just made or that you just added. So let's think about this. Let's look at this equilibrium between nitrogen, hydrogen to make ammonia. So with that in mind, the quick and dirty way, whatever we do to a reaction, it has to adjust itself to undo what you just did. So if I add nitrogen gas, if I add this, which way does the reaction have to move, forward or reverse, to reestablish equilibrium? It's going to move in which direction, forward or reverse? If we add nitrogen, it's going to move forward, because if we add nitrogen, it doesn't like that. And so if we add nitrogen, it's going to move forward, because if we move forward, we consume some reactants to get rid of some of that nitrogen we just added, right? Okay, what if it's the same reaction, but this time we remove ammonia? So we're removing a product. I like to think, if we remove product, we're making this deficit, so the reaction has to adjust itself by moving in which direction? Forward. Yeah, I just removed some product. The reaction doesn't like that, so it's going to move in a way to make up for that product that you just moved. So both of these examples are ways that the reaction adjusts itself to reestablish its equilibrium. And so the kind of thinking here is whatever you do to a reaction, you just adjust it so you undo what you just did. I guess another analogy is this seesaw analogy. All right, so in this seesaw, you can think of this as, okay, we have a reaction at equilibrium, but if I push down on this seesaw, or if I add more product, how can you adjust the seesaw so it goes back to equilibrium? If I push down on one side, don't I have to push down on the other side? So if I move everything in the forward direction, that's how I reestablish equilibrium. Or if I have a reaction at equilibrium, all right, and the seesaw moves in this way, I adjust it, so maybe I lift up the one part of the seesaw. Which way does the seesaw have to move, or how do you adjust to get it back to equilibrium? We have to move in which way, the forward or the reverse direction? The reverse this time, to bring it back to equilibrium. And that's basically Le Chatelier's principle when talking about changing concentration. All right, so that is the quick and dirty way. But this is what's actually happening when we disrupt a chemical equilibrium. What we're actually doing is disrupting the rate laws. right? So we got to remember what big K is. What is equilibrium? Equilibrium is, yes, when the reaction is stable, concentrations are not changing, but what's actually happening at equilibrium, remember, the forward rate law is equal to the reverse rate law. That the rate or the velocity that we're making products is the same velocity as we're making reactants. So when we change concentrations, what we're actually doing is changing the ratio of these rate laws for a moment of time until we reestablish equilibrium. All right, so let's look back at this ammonia example and think about what's actually happening on a particle level. So let's first just predict if we add hydrogen and disrupt the equilibrium, which way does the reaction go, forward or reverse? It goes overall forward, yes, so it moves to the right. Yes, when we add hydrogen, that's how it reestablishes equilibrium. But let's think about it using rate laws now, all right? So we can look at this graph and look at what's happening here. So for a moment in time, we add hydrogen. And so when we add hydrogen, the reaction moves to the product side. It moves in the forward direction. So it consumes some of that hydrogen. It also consumes some nitrogen, but at the same time, it produces product here. And so that's what we see happens over time until equilibrium is established again and all the concentrations are the same. So right here in this kind of sliver, we do see some changing happening, and that's due to disrupting the rate laws. So let's look at it in more detail here. All right, so we predicted if we add hydrogen, the reaction moves to the right. If we add reactant, the reaction moves to make more product to use up some of that reactant we just added. But at equilibrium, initially, before we added that hydrogen, the forward rate equals the reverse rate. So we can write the rate laws for the forward rate and the reverse rate, and that's what I have down here. Remember rate laws from chapter 14, where the concentrations of the reactants times your forward rate constant is equal to the concentrations of your products times the rate constant for your reverse reaction. We did this in mechanisms when getting rid of intermediates, and so that's what I have right here. Right, so here's your forward rate law and your reactants. Here's your reverse rate law with your products. So thinking about this, remember we added H2 to this reaction. So of these values in this rate law, what number is changing? Does the rate constant change? No, it's a constant. What's actually changing in this expression the moment that we add hydrogen? This value right here, this hydrogen value is increasing, right? This hydrogen concentration is increasing. So if all of these numbers are multiplied by one another, initially at equilibrium, these two sides equal one another, but at the moment we add hydrogen, what is happening? How do the rates change that moment hydrogen is added? How does the forward rate change? It increases. Yes, it increases because hydrogen concentration increased the moment we added hydrogen. So how does the reverse rate the reverse rate change the moment we add hydrogen? Does anything change? No, nothing changes. It stays the same because when we disrupted, when we made this adjustment, made this disruption, we didn't change anything, any concentrations on this side of the reaction. And so again, the moment that we add hydrogen, okay, this is a greater than sign. Basically, we're saying, oh, the forward rate is now overall larger than the reverse rate of the reaction. And that's why we see an overall shift to the product side, because just for a moment in time, your forward rate is faster than your reverse rate. And it's this idea, right, that the reverse rate stays the same is kind of counterintuitive. But if we remember our rate laws and what they mean, we can see, oh, if we add hydrogen, we're just disrupting the forward rate law, not the reverse rate law. But overall, we'll see an overall shift in the forward direction. All right, so that is how we disrupt rate laws. So let's look at another example, but a little bit different, all right? Suppose now we add more product. So we're going to add ammonia. So let's just use the quick and dirty way, predict which way does the reaction go if we add product. Should go what, forward or reverse? Forward? No, reverse. It goes reverse, all right, to undo what you just did. So let's draw the graph of what that would look like, right? So if we add ammonia, the reaction goes into the reverse direction to consume some of that ammonia that we just added. So that's what's right here. At this moment of time, I added a bunch of ammonia. So if it gets consumed, this value is going to go back down, right? But the thing is that it's not going to go back down to where it was initially. It's not going to look like this, where it goes back to its original concentration. Because we added more substance to this reaction, it's going to go back down, but it's going to end up a little bit higher than where it started initially, because there's more stuff in this reaction vessel now. So we consume some of the product, but then what also happens at the same time, if we move in the reverse direction, we can consume product, but we also produce more reactant. So the nitrogen concentration will go up, all right? And then the hydrogen concentration will go up a little bit, all right? So that is what our new graph will look like. And so we see after some time, after all of those changes happen, everything becomes flat and even again. This is how we reestablished equilibrium. All right. So once this equilibrium is reestablished, hydrogen concentration is higher than it was initially because we moved in the reverse direction. Nitrogen concentration is also higher than it was initially because we moved in the reverse direction. But what's a little bit counterintuitive here is that your ammonia concentration is also a little bit higher than what we started with initially because we added more ammonia to the system. Right? It doesn't go back to exactly where it was before because there's just more stuff in this container now altogether. All right, so that's another way to look at equilibrium. Let's do one more. Okay, or maybe two more, I don't know. Okay, suppose we remove ammonia. So let's first predict which way does the reaction have to go? Forward, yes, it goes forward. We removed ammonia, our sea salt went like this, so we gotta get it back. Oh, I guess no, it went like this. And so we gotta move in the forward direction to reestablish that equilibrium. So we're gonna move forward. So that's what's happening here. I'm trying to show that at this moment, I've removed some ammonia from the container. So if the reaction moves forward, how will this red graph change? It's going to go back up, but will it go back up to where it was initially? No, it's going to go back up, but still be a little bit lower than where it was initially because we're removing matter from this container. It's going to go back up, but not initially to where it was. Okay, so it went back up. We made more ammonia. So what does that mean about the concentrations of hydrogen and nitrogen? They have to go down because in order to make ammonia, you have to consume hydrogen and nitrogen. So our nitrogen graph is going to look like this. It has to go back down, and then hydrogen also has to go back down. Right, we got to consume some of those reactants in order to make more products. And so we see at equilibrium, hydrogen is what, higher or lower than it was initially? Lower. Nitrogen, higher or lower than it was initially? Lower. Ammonia, higher or lower than it was initially? It is lower. Even though it went back up, it's still lower than it was initially. Okay. All right, let's do another one. Okay, this one's a little bit different. So, okay, let's say we remove some nitrogen from this container. Okay, first let's do the quick and dirty way. Which way does the reaction have to shift? Forward or reverse? Reverse, yes. I removed nitrogen, so the reaction does the opposite to undo what I just did. So we're gonna move in the reverse direction to make up that nitrogen that I just removed. Okay, so which way does the reaction shift? Towards reactants. All right, and so since we remove nitrogen, remember Le Chatelier's principle is just the qualitative way we look at it, but we can also think about it in terms of rate laws, all right? The moment we remove nitrogen, we disrupt the rate laws. So which side are we disrupting? The forward rate or the reverse rate when we remove nitrogen gas? We're only disrupting the forward rate reaction. So what happens to the rates when nitrogen is removed? The forward rate initially does what? So if we're removing nitrogen, this number is changing how? It's decreasing. So that whole side of the equation decreases because nitrogen concentration is decreasing, right? So in that moment, if we are decreasing nitrogen, we can say, oh, the reverse rate now is greater than our forward rate overall, right? So how does the reverse rate change also the moment we add nitrogen? Nothing changes. And so all that's changing is that forward rate. So that one's decreasing when we remove nitrogen, but if we compare that to the non-changing reverse rate, we see that yes, this side in fact gets smaller, the overall reverse rate gets larger, all right, or it doesn't get larger, sorry, stays the same, so it's still larger than the other one, and so we see an overall, oh, the reverse rate is winning, so the reaction moves in the reverse direction, right? Because the forward rate is decreasing. Not because the reverse rate is changing at all. What a lot of students will think is they'll say, oh yeah, if we remove nitrogen, the reverse rate wins, that the reverse reaction has to happen, and it's because the reverse rate increases. That's not true. It's because the forward rate decreases is the reason that we see an overall shift in the reverse direction. So don't think just because the reaction goes in reverse that the reverse reaction is increasing. There's other ways we can get an overall shift in the reverse direction. All right, okay, so there we go. Nitrogen is removed. All right, so let's think about it maybe a little bit differently. Now let's think about in terms of Q, because all of these things are related to one another. All right, so let's pretend for this reaction K is equal to big K is equal to 0.3. It's products over reactants, you see that there. All right, so K is only good at equilibrium. So let's pretend we're at equilibrium, but at a certain moment, nitrogen concentration, we removed some gas. All right, so we remove ammonia. So if we're removing ammonia, think about how this ratio changes, right? If we remove ammonia, the ammonia concentration in the numerator gets smaller. So how does Q change? How does Q change? It gets smaller, it goes down. Yes, let's actually answer these questions. How does Le Chatelier principle predict what will happen to the reaction? So let's think about it in terms of Le Chatelier. So we're removing ammonia. Which way does the reaction shift? It goes in the forward direction, yes. And so yeah, I meant to do it in a different order here, okay? How has Q changed the moment ammonia is removed? Now we have a small number over, I guess, the same number, so Q goes down. Q goes down, so now it's smaller than K. And how did we predict how reactions shift before? If Q is smaller than K, which way does the reaction shift? In the forward or the reverse direction? In the forward direction, yeah, because remember, if Q is small, we have a small number over a large number. All right, and K is a bigger number, so we need a large number over a small number. So if Q becomes smaller than K, the reaction has to shift in the forward direction to make Q big again, so it is the same value as K. So all of these things are consistent with one another, right? How we compared Q and K, how Le Chatelier's principle predicts which way a reaction has to shift. We're just bringing the element of chemical kinetics back into it as well to complicate things. All right, so yes, all of this is consistent with one another. When we remove ammonia, we're disrupting K, creating a Q that's smaller than K. So the reaction has to shift in the forward direction to reaccommodate that. All right, let's do one more. Okay, so same ammonia thing. So here I tell you that K is 0.3. All right, so let's, given these conditions, tell me what happens to this reaction. When I put all of these things into the container, what happens, right? So the hint is, ask yourself, given these conditions, is the system already at equilibrium? It probably isn't. So how do we check if the reaction's at equilibrium? Plug them into K. All right, let's plug those concentrations into the K expression to see if we are at equilibrium. So we have to do 2 molarity squared over 1 over 6 cubed. Oh, I don't even know what that is. What is that? Okay, so this is equal to 4 over 36. 4 over 36 is equal to 0.11. So are we at equilibrium? Nope, we're not. So this value I just calculated, oh no, so 6 cubed is not 36. So this number is even smaller. You're right, that's why I hear whispering. Sorry, okay, so 6 cubed is 216. So 4 divided by that number is an even tinier number, 0.019. Still doesn't change my answer, all right? So are we at equilibrium given these conditions? No. So this value we just calculated, is this K? That is Q. This is Q. So to predict what happens to a reaction to reestablish equilibrium is we compare Q to K. So in this example, Q is what versus K? It is smaller, right? So if Q is smaller than K, which way does this reaction have to go? Forward or reverse? Forward. So what does that mean about the rate laws? If we're moving in the forward direction, that means what? The forward rate is greater, less, the same as the reverse direction? Which one is it? In order to get an overall shift in the forward direction. It would be A here, the forward rate has to be larger, faster than the reverse rate in order to get an overall shift in the forward direction, right? And so we can get that information by calculating Q. What's the ratio of products and reactants at this moment? How does the reaction have to adjust itself to get to K? And so in this way, shift in the forward direction, we need to have that forward rate be faster to make more products to get that Q to achieve, to increase to get to K. All right, so there we go, A, perfect. All right, so that was concentration. When we change concentration, how does a reaction have to shift, right? So the idea is if I add more reactant, the reaction goes forward. If I add more product, the reaction goes reverse. If I remove reactant, the reaction goes which way? Reverse, yes. Okay, so now let's talk about pressures. So this is specifically for gases, all right? Gases, all right? So here's the quick and dirty way. Okay, for Le Chatelier's principle for gases and changing pressure, all right? If we have a gas equilibrium, so this is an example, all right? A gas is in equilibrium with B gas, but there's twice as much B, all right? It's twice as much B. If we increase the pressure of the vessel, meaning that like I squeeze on the container. So I have a container, it's at equilibrium, I squeeze on it, right? I compress it. The reaction doesn't like that, all right? So if I compress the container, the reaction will try to relieve itself of that increased pressure. And to do that, it's going to move in the direction that has less moles of gas, right? You squeezed on the container, increased the pressure, so the reaction's going to respond by making less moles of gas. So in this example, A goes to 2 B's. If we squeeze on the container, which way will the reaction go? Towards A or towards B? If we want to alleviate that increase of pressure that we just produced, it's actually going to go in the direction that makes less moles of gas. So it's going to move in the direction of A, in this case, reactants, all right? All right, on the other side, if we have a reaction at equilibrium and we expand the container, all right, we give the gas particles more room to move around, all right? We decrease the overall pressure at that moment. What's going to happen is when we increase the volume or decrease the pressure, the reaction's going to adjust itself by trying to fill up that pressure that you just decreased. So you can just think about, okay, the opposite's happening here. If I decrease the pressure, the reaction's going to move in a direction that fills up that void. We want to make more moles of gas to fill up that void. So what we see here is if we expand on the container, we want to make more moles of gas. So in this example, the reaction moves in the forward direction because there's 2 moles of gas on the product side. All right? So when thinking about gas equilibrium and changing pressure, we shift the equilibrium when we compress and expand the container, right? By changing the pressure that way, by changing the volume of the container. This is a side note. We can also increase the pressure of a container by adding an inert gas, right? So if I have like, you know, a mole each of A and B at equilibrium, if I add an inert gas, I can increase the pressure of the container, but adding an inert gas actually does not disrupt the equilibrium at all. All right, because we're not changing concentrations. So that's a small detail, right? Adding an inert gas does not change gas equilibrium because we're not changing concentrations of A and B. Okay, so that is the quick and dirty way, okay? So if you expand on the container, you move in the direction to make more moles of gas. If you squeeze on the container, you move in the direction to make less moles of gas. So we do it the quick and dirty way, and now we learn it the real way. So let's do it the real way. Okay, so let's say we're going to look at the same gas equilibrium. A goes to 2B. So I'm just going to make up a K value. It's probably best for us to say Kp because we're working with gases and pressure. So let's say at equilibrium for this container we have 1 atmosphere of A and 2 atmospheres of B. So if we plug that into K, we get that Kp equals, oh, this is all weird, it's all messed up. We see that Kp at equilibrium equals 4, right, for this system. Right? I'm just making up equilibrium concentrations, okay? All right, so at equilibrium, Kp is 4. So let's take this vessel that's at equilibrium, let's squeeze it, and then let's expand it and see what happens. So let's compress on this container and use Q to predict which way the reaction has to go. All right, but first, before I move on, if I squeeze on this reaction at equilibrium, which way does the reaction go, forward or reverse? Reverse, yes, because if I squeeze on the container, I'm increasing the pressure initially, so it moves in the direction with less moles of gas. Let's see if Q predicts the same thing. Do you think it'll predict the same thing? Yes, it will. Okay, so let's compress on the container. So let's just make it easy and say that the volume of the container halves. We go from, 2 liters of volume to 1 liter of volume. So if we halve the volume of the container, how does the pressure of A change? We were initially at 1 atmosphere. Now what are we at? 2 atmospheres, yes, because we halved the volume. Remember Pivnert here, PV. And one instance is equal to pressure volume in your second condition, all right? So if we have the container, have the volume of the container, our pressure doubles. Okay, if we have the volume of our container, the pressure of B was initially at 2 atmospheres. So what is the new pressure now? Not 1, it's, so we're initially at an atmosphere of 2 atmospheres. Okay, we're squeezing on the container, less volume, so we're doubling its pressure, right? Because when we squeeze on, when we decrease our volume, we double pressures. Or you can think, oh, if I have the volume of A, pressure doubles. If I have the volume of B, pressure doubles as well. So here we see, B now has 4 atmospheres of pressure. Both of them double because we have the volume. Both of them. Okay. So this is our new concentration. So let's go ahead and calculate Q at these new concentrations. So what is Q now using 2 and 4 atmospheres? So remember our equation for K is pressure of B squared over A squared. So Q is now, what is that? 4 squared over 2, which is what? 8. Okay, so Q is now 8. Yeah, 16 over 2. Yeah, okay, all right. So Q is now 8. And so now Q is what versus K? It is larger than K. And so what do we say when Q is larger than K? Which way does the reaction shift? In the reverse direction. Is that exactly what we predicted? For when we squeeze on a container, we move in the direction that makes less moles of gas. And so yes, that is consistent here. All right, moves in the reverse direction. All right, let's do it the other way. Let's expand on the container. All right, so let's go back to equilibrium. 1 atmosphere of A, 2 atmospheres of B. If I expand on this container, which way will the reaction go? In the forward direction, yes. So that's what we're going to predict, and hopefully Q predicts the same thing. So if we double the volume of this container, pressure has to change. Pressure has to change. So if we double the volume of the container, A concentration will go from 1 atmosphere to half an atmosphere, yes. All right. B pressure, the partial pressure of B, if we overall double the volume of our container, is going to go from 2 atmospheres to 1 atmosphere. All right, let's calculate the new Q using these pressures. It's still B squared over A, so it's going to be what? 1 squared over a half. So Q now, not 0.2, a half. Q now is what? 2? Is that right? Q is 2, and that is what? Bigger or smaller than K? Smaller than K. So what does that mean? Which way does the reaction have to go if the reaction is smaller than K? Yeah, it moves forward. And is that exactly what we predicted with using the quick and dirty way? Yes, it is. And it's because when we change the volume of the container, right, we're changing the partial pressures of all of your gas reactants and products. And what happens is that the value of Q changes. And so Q has to adjust itself to reestablish K. And so yes, we do see that the reaction does move forward. And it matches exactly the quick and dirty way we did it earlier. Okay. So in this example, we see when the number of gas particles on the products and the reactant side are different. When we squeeze and expand on our container, we see that, yes, equilibrium is disrupted. So, of these, which equilibria do you think are unaffected by volume changes? So in your head, squeeze on all of these containers. In your head, squeeze on them. Do any of these reactions, are they unaffected by volume changes, by these pressure changes? What do you want to be looking for? The idea here is when we squeeze on the container, the reaction moves in a direction that alleviates that increased pressure. But for one of these reactions, it's, there's a detail, right? So squeeze on this container. If you squeeze on this container, which way does the reaction go? Reverse, because there's 1 mole of gas here. There's no moles of gas here. So to alleviate, it's going to go reverse. Okay. What about this one? Which way will the reaction go if you squeeze on it? It's going to go forward or reverse? Reverse also, because you want to make less moles of gas to alleviate that increase in pressure. All right, what about C? Which way will the reaction go to alleviate squeezing on it? Forward, yeah, because there's 2 moles of gas on the reactant side, while only 1 mole of gas on the product side. All right, so hopefully it's the last one. So what happens to D when you squeeze on it? Is there any way the reaction can move to alleviate that increase in pressure? No, because both sides of the reaction have 2 moles of gas. All right, 2 moles of gas. So D is the only answer here. This is the example where delta N equals 0, where squeezing on it, there's no way we can alleviate that pressure. If we expand on the container, there's no way to make more moles of gas because we have the same number of moles of gas on each side of the equilibrium. So this equilibrium, if we change the volume of the container, the equilibrium is going to be unaffected, right? Because the pressures, they're changing, but they're changing equally. So we don't see changes in Q at all. K just stays the same here. Right? And in this example, yeah, what we're looking for is where delta N is 0 basically there's no difference in moles of gas on each side. So that one is unaffected by changes that we talked about previously. Okay, so that is gases. That is gases. So let's move on to the last one. How else can we disrupt equilibrium? This one's my favorite. Okay, temperature. Temperature can affect chemical equilibria as well, but for a little bit of a different reason versus the other ideas that we looked at before. All right, so let's learn it the quick and dirty way and then learn it the right way. All right, so let's do the quick and dirty way first. So when we change the temperature of a equilibrium, our equilibrium is adjusted. Okay, so the quick and dirty way to treat temperature changes is we want to know what the enthalpy of the reaction is, meaning is it endo or exothermic? That's what we want to think about. And then just treat heat as a reactant or product, and then treat it the same as concentration. So in an exothermic reaction, or sorry, no, endothermic. Endothermic reactions, if you hold an endothermic reaction, what does it feel like? Endothermic? Cold. It should be cold. So is heat a reactant or product? It's a reactant, yes, because the reaction is stealing heat. Who's it stealing it from? You, stealing it from you, and that's why it feels cold. So heat, and I'm just going to use triangle here, it's a reactant. Okay, so an exothermic reaction. Exothermic reactions feel hot. So is triangle a reactant or product? It's a product. Okay, cool. So this is the quick and dirty way. Just treat heat as a reactant or product. So if you add heat to an endothermic reaction, which way does the reaction go, forward or reverse? Forward, yeah. It's just think of it as a reactant. You're adding a reactant. Versus if you take an exothermic reaction and add heat, which way does it go? Reverse, because if triangle is a product and you add more triangle, it's going to go in reverse. All right, that's the quick and dirty way. All right, so let's look at this example, and this might help you. I know you did SOL like a while ago, but hopefully this slide will help us think about solubility of solids and how it changes with temperature. So the dissolution of calcium hydroxide is an exothermic process. So where does triangle go? On the product side, yes, okay. So remember, we're just doing it the quick and dirty way. So let's just treat heat as a product or reactant. So in which direction will the equilibrium shift? If we heat this vessel, it's going to shift in the reverse direction. But if we cool the vessel, remember, triangle is a product. If we add heat, we add triangle. So if we remove heat, we are removing triangle. Okay, so if we cool the container, we're literally just removing this part of the products on this in this equilibrium. So if we cool the container, we are removing triangle. Which way does the reaction shift? To the forward direction, yes. Because we're removing a product, essentially. Okay, so based upon those observations, the reaction moves towards the reactant side when we heat it, but towards the product side when we cool it. What do we think? Is calcium hydroxide more or less soluble at high temperatures? At higher temperatures, all right, the reaction shifts in which direction? The reverse. So what would our eyeballs observe if we heat it? We would see more solid fall out of the solution. So is calcium hydroxide more or less soluble at high temperatures? It's actually less soluble at higher temperatures because adding heat to an exothermic reaction moves it in the reverse direction. So when we move this reaction to the reverse direction, we produce more solid. We don't dissolve more stuff, we make more solid, right? And so that's where the idea of, okay, is it an exo or endothermic reaction? Just treat triangle or heat as a product or reactant can help us predict whether something is more or less soluble at higher temperatures. Okay, let's do an endothermic example. Where does triangle go? It's a reactant this time. So if we heat KCl, a saturated solution of KCl. Which way does the reaction go? Towards the product. So forward. If we cool it, it goes which way? Reverse. Perfect. So is KCl more or less soluble at higher temperatures? More soluble, because adding triangle turns solid into aqueous. That sounds like dissolving. You dissolve more at higher temperatures. All right? Okay, so that explains SOL. We can simply just think of triangle or heat as a product or reactant when we're given the idea is it an exo or endothermic reaction. Okay, so let's do an example. Okay. So let's look at this equilibrium, a violently colored iron thiocyanate complex is red. So the product here in this equilibrium is red versus the free iron ion is yellow, right? So here's the equilibrium, right? And so I am showing you two different situations. Here is the container when it's hot. Here it is when it's cold. Using these observations, can you tell me, is this reaction as written endo or exothermic? So the strategy here is just figure out where triangle goes, given these observations, all right? So let me ask you this. All right, so here's our reactant is yellow, our product is red. So when we are in the hot water bath, what is mostly present, reactant or product? Reactant, because it's yellow. But when we're in the cold water bath, what is the thing that's most present? The product. Okay, so can you tell me where triangle has to go to be consistent with these pictures? Triangle is what, a reactant or product? Product? I don't even know, I gotta test it. Here's the thing, just put triangle somewhere and test it in your brain and see if it's consistent with what we see. So if we put triangle as a product, adding heat will shift it which direction? In the reverse direction. So if we heat it, the solution should become what color? Yellow. And is that what we see? Yes. Versus if we cool this reaction down, it shifts the reaction in which direction? The forward direction. Yes. And so if we cool it down, remove triangle, the solution should turn blood red. And is that what happens? Yes, it is. So here, we could just guess where triangle goes. All right, let's just pretend we put triangle over here. All right, and in your mind, just add heat, remove heat, and see if it's consistent with the pictures that we see. So I'm just putting triangle on the wrong side intentionally. And so we see, if we add heat, we should see the solution turn what color? Red. It should turn red. If we add heat, it pushes towards the product, but is that what we see? No. So that means that triangle is on the wrong side. So triangle should be over here. Okay, so triangle's on the product side. So tell me, is it exo or endothermic as written? This is what kind of reaction? Exothermic. Yes, it is exothermic, right? Yes, I like iron thiocyanate. It looks like blood, right? And what is blood made out of? Hemoglobin. What's on the inside of blood? Iron, yes. Okay. All right, so let's put it all together. All of the Le Chatelier principle stuff together. And then we'll learn the temperature ones the real way, because we just did it the quick and dirty way. Okay, so let's consider this exothermic process of the ammonia thing again. So that's an important piece of information. Exothermic tells us where triangle goes. So where does triangle go for this reaction? It is a product. Perfect. Okay. And that'll be useful if we have to change the temperature. All right. So what direction does the equilibrium shift if we increase nitrogen concentration? It goes which way? Forward or reverse? Forward, yes, because we're adding a reactant, we make more products. What if we decrease the amount of hydrogen? Which way does it go? Reverse, yeah. So again, if you think of like a seesaw, it'll help you. All right. What if we take HCl, add HCl to this reaction, which neutralizes ammonia? So essentially, we are removing ammonia. We remove ammonia. So what do you think is going to happen? Forward, yeah. It's just like, it's a special way of me saying, oh, you remove ammonia. But we are removing it by neutralizing it with an acid. Okay, perfect. All right, what if we double the pressure of the reaction vessel by squeezing on the container? Which way does it go? Forward or reverse? Squeeze on the container. Forward, yes, it goes forward, because what do we want to do when we squeeze on the container? Make less moles of gas, less moles. And so we see, oh, there's only 2 moles of gas on the product side, 4 moles on the reactant side. Okay, what if we double the volume of the container? Doubling the volume of the container lowers the partial pressures. So if we double the volume of the container, we want to make more or less moles of gas. More. So we shift in the reverse direction. We want to go into the direction with more moles of gas. So in this case, as written, it's in the reverse direction. What if we add an inert gas to the container? What happens? Nothing happens. Yes, nothing happens. So this one, 6 is different than 4. 6, you might think, oh, but you increase the pressure of the container, but it does not disrupt the partial pressures of anything. But squeezing on the container increases all of the partial pressures of your reactants and products. So that's the difference here. Okay, what if we heat the reaction vessel? Which way does it go? Forward or reverse? Reverse, yes, because now we're just essentially heating it means adding triangle. We're adding a product, okay? Versus cooling the container shifts it which way? Forward, because we are not adding triangle, but we are removing triangle instead. So treating it like a reactant or product, right? Le Chatelier's principles are like my favorite because it's all consistent. You learn it the quick and dirty way. You look at it using a real method, and it all works out there. All of it's consistent with one another. Okay, so let's look at these last 2, right? Heating and cooling the vessel. We added versus removed triangle to predict which way the reaction shifts. But I'm here to tell you that the real way to treat shifting equilibria with temperature is that we're actually changing the value of K when we change temperature, right? So quick question. When we did the other ones, these ones, when we increase nitrogen or decrease ammonia concentration, when we change concentrations, do we change the value of K? No, we just change Q. When we change pressures, when we expand or compress on our container, we're just changing Q. We're not changing the value of K. But when we have temperature involved, we do actually change K. And that's why we see a shift in equilibrium. So here's the last one, the real way to treat equilibria shifting with temperature. Remember, K is equal to products over reactants, right? Concentration products over reactants. But what is K also equal to? The ratio of the rate constants. All right, the ratio of the rate constants. So when we change temperature, what we're actually doing is changing the rate constants that is also equal to K. So let's remember, K is equal to the forward rate constant over the reverse rate constant. Do you remember the Arrhenius equation? You remember this guy? All right. Rate constant, little k, is related to activation energy. Little k is related to temperature. So what were the trends back in chapter 14? K would increase when either temperature increases, that's how you make reactions go faster, but also when activation energy is small, reactions go faster. All right, okay, so, but what else did we say about rate constant? Okay, when we did the 2-point Arrhenius equation, we get bigger rate constant increases when your delta T is large. So if you're changing the temperature a lot, you'll see a big rate constant increase. But also, what else did we say about rate constants? It's related to activation energy. If your reaction is already going fast and you heat it up, does it go faster? heating up reactions always makes it go faster. But if the reaction's already going fast, if you give Jeff Bezos $5, does he get richer? Yes, but by a lot? No. But if you give me $5, okay, I get richer, but I get richer in a larger ratio, right? So here's the idea, that when a reaction is already going fast, right, increasing temperature is going to affect it less so than if the reaction's already going slow. So what we're doing when we increase the temperature of a reaction, an equilibrium, the forward direction increases, the reverse direction increases, but they increase unequally. So can you tell me, of this equilibrium, this is an endothermic example. So tell me, in an endothermic example, which direction is, has the larger rate constant? The forward direction or the reverse direction? This is a chapter 14 question. Which can you get over faster? The reverse direction. So we see the reverse direction has a larger rate constant than the forward rate constant, okay? Forward. So if we heat up this reaction, does the forward rate constant increase? Yes. Does the reverse rate constant increase? Yes. But do they increase the same? No, they don't. So, okay, what happens to forward? It increases. Reverse increases. But which one increases more? The forward increases more because it's already going slow. Right? Okay, so if forward increases, reverse increases, but forward increases more, how does the KF-KR ratio change? Because remember, that is the equilibrium constant. That number, K gets larger, all right? KC gets larger. KC gets larger. Because the forward reaction rate constant increases more, because it has a larger activation energy. All right, let's see if this is consistent with Le Chatelier's principle. So what's Le Chatelier's principle for endothermic? It's reactants go to products, but triangles a what? It's a reactant. So just do it the quick and dirty way. All right, add triangle. Which way does the reaction move? Forward. But the real way is, if you increase temperature, you actually change your rate constants. The forward rate constant increases more, making K a larger number. So if K is a larger number, you produce more what to make K larger? You produce more products because K is also products over reactants. So it's all consistent with one another. Yes. Okay, so let's do the other. So we did endothermic, now let's do exothermic. Okay, so let's, real quick, for an exothermic reaction, triangle's a what? It's a product, yes. So quick and dirty way, add triangle, which way does the reaction go? It should go in the reverse direction. So let's see if all of this is consistent with one another. So remember, increasing temperature always increases rate constant, but if the reaction is already slow, it increases more. All right, so here's an exothermic example. If we compare the forward and the reverse rate constants, which one is slower, forward or reverse? Reverse, because the reverse is a bigger hill. It takes me longer to get up that hill. So K reverse is small, but K forward is really large. So if we heat up this reaction, does the reverse rate constant increase? Yes. Does the forward rate constant increase? Yes. But which one increases more? Reverse, yes. So forward increases, reverse increases, but reverse increases more because it is already slow. It's already slow. So what does that mean about the new forward over reverse rate constant ratio? That number actually changes how? It gets smaller because now we have a larger number in our denominator. So Kc actually goes down. It becomes a smaller number. How do we make numbers smaller? We put bigger numbers in the denominator. So if we have a bigger number in the denominator, what do we have more of at equilibrium at higher temperatures? More reactant. Is that consistent with Le Chatelier's principle? Where if we heat an exothermic reaction, which way does the reaction shift? To make more reactant. And so that is consistent with, okay, heating an exothermic reaction makes the equilibrium constant a smaller number, meaning that there's more reactant present at equilibrium. See how it's all consistent? I love it. I love it. And it includes rate constants. Okay, perfect. Okay, so there we go. That's the real way to treat shifting equilibria. Changing temperature actually changes the value of K. And what we're doing is changing the ratio of the rate constants and relating that to a difference of activation energies of the forward and the reverse rate constants. Or sorry, a forward and the reverse reaction coordinate diagram. Right? Okay, so, okay, one more here in this one. So let's just look at this reaction profile. All right, here's our forward rate constant. There's our reverse rate constant. So what do we think happens when we heat this reaction? When we heat this reaction, what happens to the forward rate constant? It increases. Heating stuff always increases rate constant. But what happens to the reverse rate constant? It also increases. But does one increase more than the other? No. So in this case, they increase the same because the activation energies are the same. They both should have the exact same rate constants here because activation energy is the same. So for this reaction, so this one's neither endo or exothermic, do you think Kc, our equilibrium constant, will change? No, they do not change. They don't change at all because the ratio stays the same. So will an equilibrium shift if we have a reaction that's like this and we increase the temperature? Will we see a shifting to products or reactant side? Nope, no shift. No shift at all. Okay. All right, so that's chapter 15. So we got like 9 minutes, so I'm going to just show one last demo, putting it all together, and then we'll end there. Okay, so here is one more demo. Another one with temperature. So this one is a equilibrium between N2O4 and NO2. So this is a cool demo because these are gases. And what's nice is that these gases are colored, so you can tell what's present. So right now, at room temperature, what color is this? It's brown. It's brown. So what is mostly present right now? Which thing? Product or reactant? Product. I got to check. Yes, because the product is brown. All right, so I'm going to put one of these in a hot water bath and then one of them in a cold water bath, and we're going to predict whether this reaction is endo or exothermic. So we're basically doing what? Trying to figure out where we need to put the triangle to be consistent with our observations. Okay, so it's already happening. All right, so do you see a color difference now? Yeah, a little bit. So we see in this is the hot water bath. The hot water bath is making more what? The product, yeah, the brown thing, whatever the brown thing is, right? Versus the cold water bath, it's getting lighter in color. So which way is the reaction shifting in the cold water bath? Towards the reactants. So tell me, where does triangle go? If you don't know, just guess and check and test. So I think, so in the hot water bath, we're making more product. So if we put triangle right here, add heat, it should turn what color? Brown. Is that what we see? Yes, it is. So this reaction is what? Endo or exothermic? Endothermic. Very good. It is endothermic. Okay, yes. So it turned hot, or in the hot water bath, it turned brown. So we see, oh, triangle has to go on this side to produce that that observation. And so as written, this reaction is endothermic. If I wrote it in the reverse direction, it would be an exothermic reaction. So I have to specify in the direction that it's written. Okay, so we are, as temperature increases for this reaction, how does K change? Because remember, changing temperature changes the value of K. So how is it changing? Is K increasing or decreasing? It is increasing. Yeah, you can also think about it this way. At higher temperatures, it becomes more brown. Brown comes from which thing? The product. So in order for the equilibrium constant to be consistent with that, make more product, we have a bigger number in the numerator. So K has to be a bigger number. All right, but why does K change? Is it because the forward rate constant increases what? More or less than the reverse rate constant? Yeah, so maybe just draw it. Draw what an exothermic reaction coordinate diagram looks like, where your product is what? Higher or lower than what you started? Exothermic. Oh, no, sorry, this is endothermic, sorry. Endothermic. You're higher than where you started. So tell me, which direction goes faster? The reverse direction. So if we heat this up, which direction increases more? The forward. So we see that the forward actually increases more in this example than the reverse, and that's consistent with the idea that our equilibrium constant is products over reactants. When we heat it, we make more of the brown thing. When we heat it, this number, forward, increases more than our reverse rate constant. All right, so both of those relate to an increase in our K value. All right, so that puts it all together. I guess last one, so that's all temperature changes. What if I squeezed on this container? What color would it turn? If I squeezed it real hard, will it turn more brown or will it turn more colorless? It will turn which way? Colorless, yeah, because if I squeeze on the container, that's increasing the pressure. Increasing the pressure, I want to make less moles of gas, so I want to move in the direction with less moles of gas. So squeezing on it would make it turn more colorless. All right. Okay, so that's it for chapter 15. So chapter 15 homework is due on Monday, yes, Monday. And we'll start 16 next week.